Okay, so here we try to argue that if the moving charge are positive, what it will be, okay? What will be the contradiction? What will be the contradiction? Okay, so follow this figure, okay? We try to draw out a simplified one. Okay, here we assume that, okay, the current I also pointing downward, just as the uppercase. We still have the B field pointing into the page. I don't draw it inside, but assume there should be some B field inside the strip. Okay, so here, rather than a positive charge moving upward, it should be positive charge moving downward, okay, so that the current will be equivalent. Okay, so if it is VD pointing downward, and then this is a positive charge, okay, so Q is positive, and then V is pointing downward, and then cross into the page. So your thumb will be pointing to the right side, okay? VD and then cross into the page. Your thumb is pointing to the right side, and then it is a positive charge. So FB is pointing to the right side. Okay, actually the same as the previous case. So in this case, positive charge start to accumulate on the right side, and then there should be negative side on the other side. Okay, so in that case, of course, we should have a E field pointing to the right side and then pushing, pushing the positive charge back. But actually, based on the experiment, the polarity, okay, the polarity here, okay, positive on the left side, negative on the right side, it does not match this polarity of the Hall effect potential. So which means that this polarity, the polarity of the V contradicts with the experiment. Okay, so which means that it cannot be possible that the moving charge are positive. Okay, so this is the very first experiment to really prove that, okay, the moving charge inside the circuit should be negative charge. Okay, so here we have a sample problem. So here it says a solid metal cube, okay, solid metal cube of edge length D moving in the positive Y direction in a constant velocity V, okay, so this is the positive Y, okay, so this is V. Through a uniform magnetic field, a uniform B field, okay, so uniform B field onto the positive C direction with a magnitude of this value. So which cube face is at lower electric potential, and which is at higher electric potential? Of course, the opposite side have a higher of the motion through the field. Okay, so here let us first try to think, okay, which sides have a positive or has a higher potential, higher electric potential. Okay, so the idea here is like we have a cube moving upward. Which means that there will be some electron. Okay, of course there are some electrons inside the cube, which is free to move. Other nuclei are just fixed as a specific topology of a specific structure. So only the negative electrons, okay, the negative charge electrons are free to move. Okay, so here we try to moving this whole thing upward, which means that the moving charge, okay, the moving charge are moving upward. So it still follow V cross B. V is positive Y direction, Z is like out of the page. So your thumb is pointing to the right side, so to the right side, but this is negative charge, so the charge will go to the left side. Okay, FB goes to the left side. FB goes to the left side, which means that all the electrons are concentrated on the left side, and conversely, for the right side, it will have a positive charge, which means that for lower, okay, the left side is at lower potential, and then for the right side is at higher potential. Okay, the right side like this. Okay, so yeah, so for question B, it asks you what is the potential difference between the phases of high and lower electric potential. So we actually make use of V equals small v times B times D. So V is 4 meters per second, so 4, and then B is 0.05, and then 1.5 centimeter for D, 0.015 meter. So this is 3 millivolt, okay, 3 millivolt, which is not high, but actually it is measurable. And of course, this is not the same as this case. This case, we try to generate some current by some battery, so that there will be some moving charge of the wire. The wire doesn't move by itself. But here, we don't provide any battery. We only have a cube, okay, have a metal cube, and then we try to move it in the B field, through the B field. So and we still have this Hall effect. Okay, so here we have a circular charge particle. So in this case, we only have a uniform B field. So here it says a beam electrons is projected into a chamber by the electron gun. Okay, so this is the or maybe I use this color. Okay, this is the electron gun G. Okay, so the electron gun enter the plane of the page with speed v, which means that the v is like this. Okay, the v is like this, and then move in a region of the uniform B field and direct out of the page. Okay, so the B field is pointing out of the page. As a result, Lorentz force, okay, the Lorentz force Fb blah blah blah, and continues deflect the electron, and because Vb are always perpendicular to each other, this deflection causes the electrons to follow a circular path. Okay, so this is like circular motion. Okay, circular motion from here to here to here, going back. Okay, I don't draw it really well. So, but actually this is a circle. You assume it is a circle. So the path is visible in the photo because atom of gas in the chamber emit light when some of the circular electrons collide with them. Okay. Okay, so there is some light. Okay, of course it becomes weaker and weaker. So it only shows part of the path. Okay, so here apply the Newton's second law to the circular motion use QVB. Okay, QVB. Okay, so actually when you learn the mechanics, okay, so this is the F. Okay, so F, this is the F. Okay, equals QVB. Okay, we assume all the vectors are, the V and B are perpendicular to each other. So this is F. Okay, according to Newton's second law of motion, which is ma. F equals ma, and then for the circular motion, A is V squared over R. Yeah, actually you should have learned it in high school physics. So we have QVB equals mv squared over R, and then we can actually solve R. Okay, solve R. We try to move QVB to the right side and then cancel the V with the V squared partially. So finally we have R equals mv over QB. And then later we also will make use of the period of the circular motion, which will be like T equals 2 pi R over V, 2 pi R over V. So which is like 2 pi over V times mv over QB. And then we cancel V and V, it turns out to be 2 pi m over QB, something like this. Okay, so this is the period of the circular motion. Period of the circular motion. Yeah, so later on we will make use of both of this one and also this one. Okay, for this sample problem. So here it says an electron with a kinetic energy, okay, 22.5 eV move into a region of uniform B field of magnitude, this value, and the angle between the direction of B and electron velocity is 65.5 degrees. They are not perfectly perpendicular to each other. So here is this is the direction of V, this is the direction of B, okay, and then this angle is 65.5 degrees. So which means that we can decompose it into this one is the perpendicular component. Okay, I mean this component perpendicular to the B field, and then this is perpendicular to the B field. Okay, so what is the pitch of the helix path? Okay, helix path taken by the electron. So the helical path means the 螺旋线。这个常常考试或者是 quiz 的时候，有同学会问相关的，那就表示应该没有上课，或者是连复习可能都没有，就会问哦，这个 helix 是什么意思？然后 pitch 是什么意思？那可能连这个例题也没看过。Okay, so actually, what is the pitch? Okay, so the pitch means that, so actually, why it will look like a helix path? We can actually decompose it into two, decomposite the V into two parts. So which means that for this one, it has no, it has no interaction with the B field. Okay, correspond to this V parallel. So which means that in this, let's say this is a z direction, this is z direction, suppose this is z direction. Okay, so this charge is uniform. This charge is moving uniformly. Okay, with a uniform speed. Okay, it doesn't change at all. And then in the xy direction, as much as this v perpendicular is perpendicular to the B field, so that in the xy plane, okay, in the xy plane, it will have circular motion. So which means that in xy plane it is circular motion, but in z direction it is moving upward uniformly. So it will be like a helix line. Okay, it will become a helix line. So actually, if you seeing it from the top, okay, it is still like a circle. But if you just seeing it from the side, okay, it is just like okay, moving upward. Okay, moving upward. And then for the pitch, which means that as much as it is a circle, so actually all this center will become the axis of this helix. And then if we try to pick a point here and then draw a line perpendicular to the axis, it will go to the helix line, okay, by one level, okay, one level. So for the adjacent point, okay, so this distance is called a pitch. This distance is called a pitch. Okay. Yeah. So So here, of course, we know the kinetic energy. So first, we need to calculate the velocity. Okay, the velocity, which is square root of 2k over m. So this 2k is 2 times 22.5 EV, okay, and then we need to multiply it by 1.6 times 10 to minus 19, and then over the mass of the electron is 9.11 times 10 to negative 31st. Okay, so this is 2.81 times 10 to the 6th power meter per second. Okay, so actually the pitch, okay, the pitch will be like V parallel, because in this direction, it is actually moving like V parallel. But how much time it takes? It is like a period. It takes a period of the circular motion so that it moves up in this z direction. Okay, so multiply by this period. Okay, so just as what I derive here. Okay, so the period is actually 2 pi m over qb. So this V parallel will be V cosine of phi. Okay, so this is V parallel, and then also 2 pi m over qb. So we can plug in the values. V is 2.81 times 10 to the 6th power, and then cosine of 65.5 degree. Okay, so this is V phi, and then 2 pi m is 9.11 times 10 to negative 31st, and then yes, okay, this is 1.6 times 10 to negative 19th, and then B field is where is B? This one, okay, 4.55 times 10 to negative 4th. Okay, so this is 9.16 centimeter. 9.16 centimeter. Okay, so this is the pitch. This is the pitch of the helix. So far, any questions? Okay, so if no, move on. So we have another sample problem. So here it says the essential of a mass spectrometer. Essential mass spectrometer. 叫做质谱仪啊，质谱仪 ，OK, which can be used to measure the mass of an ion, OK, mass of an ion, ion of mass m and charge q, and charge q is produced in source S, OK, which means this is the source, OK, this is the source. It will shoot out an ion. Okay, here we assume the ion is positively charged, and then it will be accelerated by this potential. Okay, so actually we assume that here the potential V, potential energy U is 0 here. There will be some final U, okay, UI, UF, something like that. Okay, so UF will be like Q times V, something like that, or negative QV, depends on what you like. Okay. So the initial stationary ion, okay, initial stationary ion is accelerated by the electric field due to the potential difference V. Okay, so it will accelerate the positive charge up to this point and then enter the region of the uniform B field. So the ion leaves S and then enter separate chamber, blah blah blah, perpendicular to the path of ion. And then a wide detector lines of bottom wall of the chamber and then cause the ion to move in a semicircle. Okay, originally it should be a circular motion, but we only enter it here and then it will stop at this wall. Okay, it cannot really go through, okay, as a whole circular motion. So it will only be a semicircle and thus strike the detector. Okay, so here we try to measure the distance. Measure the distance here, x. Okay, we can measure the distance x, and then suppose the value b, v, q are these values, and then the x is these values. So what is the mass m of the individual ions in atom mass units? So we just try to divide the mass in kilogram by this value to be 1 U. Okay. Okay, so here we first try to make use of the conservation of energy. Conservation of energy, which means the kinetic energy plus the potential energy is the mechanical energy conservation. Okay, so we can actually write it as delta K plus delta U to be 0. So which means that the kinetic energy change, and then the potential energy change adds up to be 0. So one is increased, one is decreased. So of course this one increased, this one's decreased. This one, okay, originally stationary, so which means that initial kinetic energy is 0, and then finally it becomes half of mv squared. And then for the potential energy, initially is also 0, and then finally becomes positive QV. Okay, so the delta V, okay, I mean should be negative. Okay, should be negative QV. So the delta U should be negative QV equals 0. So here we can have V equals 2QV over M, and then take the square root of the whole thing. So making use of the conservation of energy, conservation of mechanical energy, we can find the velocity. Velocity. Yeah, actually Q is known, V is known, also M is known. Okay, so all the values known, we can actually calculate the V. And then finally, we can calculate the R. The R, okay, the R is given by mv over qb. Okay, just as what we get. Okay, this formula we already get it previously. So we can just plug in m over qb, and then the v is actually 2qv over m, and then the square root of this term. So we can have 1 over b in the front. Okay, this 1 over b goes to here, and then 2. Okay, 2 goes to here, 2 goes to here. And then Q and Q partially cancel. So Q and Q partially cancel, go to the denominator inside the square root. M and N also partially cancel, goes to the numerator. And then the V remains there. Okay, something like that. Okay, so actually we know x. Okay, x is the parameter rather than the radius. So which means that x is actually 2r. So which is 2 over b times square root of 2mv over q. And then finally we can solve m. Okay. So by squaring both sides and then moving the terms, okay, so it is actually x squared and then times b squared and then times q over 8v. Okay, so this is just some algebra. So we can plug in all the values. X is 1.6254 square, and then times B is 80 times 10 to negative third power quantity square, and then Q is 1.6022 times 10 to negative ninth power, all over 8 times 1000. So this is nothing but 3.3863 times 10 to negative 25th kilogram. And then it asks you to represent it as the unit, okay, mass unit, which is like the mass of a proton or a neutron. Okay, so this is nothing but 203.93 U. Okay, roughly 204 U. Okay, psi 3 less than 204 U. So which means that the number of proton and electrons adds up to be 204. Adds up to be 204. Maybe you may ask why it's not perfectly 204. Yeah, because there are some mass loss. Okay, there will be some mass loss. So there will be nuclear action. So I don't go too deep. Okay, so actually it is actually related to E equals mc squared. So there will be some mass loss. So if you can have some nuclear action, then it can release some energy. so on average, the lightest element per proton and neutron in the nuclear will be the iron. Okay, will be the iron. Okay, so for the any element, okay, have a higher index than the iron. Okay, we'll have the we'll have the核裂变. Okay, we have 核裂变. Okay, so it will try to releasing some mass. Okay, so and then okay, so some mass will be transferred to the energy, and then for the so for the element have a lower index than the iron, then it will have the 核聚变. Okay, so so it will like the index of the element will increase from helium, from hydrogen, helium, so on and so forth, up to the iron. Okay, so finally end up if just like if a planet is mainly constructed by the iron, then it will be quite stable. Yeah, so here we talk about some particle accelerator. Particle accelerator, 粒子加速器 accelerator, particle accelerator. Yes, so we will learn two types. One is called a cyclotron, and the other one called a synchrotron. The cyclotron is 回旋加速器. Okay, the cyclotron, the figure is top view, blah 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 blah. Yeah, so actually it has two hollow D shape. Okay, just like here. Okay, so this is one of the D shape, this is another D shape. Okay, so starting from the center. Okay, and then it will try to go from here and then like this, and then accelerate gradually. Okay, and then up to here it shoot out. Okay, so let me try to explain what is happening here. So actually there will be a small gap. Okay, there will be a small gap. So here let me try to only draw these two lines. Okay, so roughly like that. So at the very beginning, it is the point S in the middle. Is the point S in the middle. So there will be B field in these two D shape. Okay, so there will be B field. Okay, there will be B field. Pointing out of the page, and then it is uniform B field. Uniform B field. So which means that we have B field on the left side, B field on the right side also, but no B field for the gap. No B field for the gap. So for the gap, we try to generate some E field alternatively. So at the beginning, okay, it will be like the E field is pointing to the left side, and then we also assume that this particle is a positive charge. So which means that it will accelerate up to this point. Okay, so there will be, let's say this is V. This is V at the beginning. Okay, so this V, okay, and then we won't have E field for the left side and the right side. So which means that this is the initial initial velocity entering a uniform B field which is perpendicular to it. So there will be a circular motion for this half of circle. So up to here, the speed will be uniform up to this point. So okay, so this is only for this part, and then for here we will generate. Okay, we will swap the direction of the E field. Swap the direction of the E field, and then the E field will be pointing to the right side. The E field will be pointing to the right side, so that the velocity v here will be accelerate up to this part, becomes, let's say, v prime. Okay, so here v prime is larger than v. Okay, if we swap the E field correctly. So in this case, as much as v is larger, so here, according to this formula, this is a constant, this is also a constant, this is also a constant. So which means that if v is larger, r is larger. So here it becomes something like this. Okay, so this will be v prime at this point. Okay, so this E pointing to the right side only for this part. So here we will also make it like E is pointing to the left side. E is pointing to the left side. So which means that, okay, this particle will further accelerate up to this point v double prime, and then repeat it again, and then v double prime is even larger. So the radius is even larger. Up to this point is v double prime, and then so on and so forth. This particle will be accelerate gradually. So yeah, so this E field is alternating between left and right with a period f. Okay, with a period or with a frequency f oscillation. Okay, with a frequency. The period should be the reciprocal of the f. So for this topology, it is easier to control. We only need to switch between the E field frequently, then it will be okay. But the weak point of this structure is that it can generate the particle with low energy, which is less than 50 mega eV. Yeah. So because the idea is like we need to generate the B field for these two area, for these 2D shape. Actually, generating strong B field in large area, we need a huge amount of energy. Actually, this D shape would be really large. So generating B field in the whole area will be power consuming. So it is not easy to achieve high energy with this particle accelerator, with the synchrotron, with the cyclotron. This is cyclotron. Okay, so we have the synchrotron. Okay, so we will not go deep, but yeah, so I just try to briefly introduce it. So we have the proton synchrotron. So this is not a disk anymore. So the proton will follow a circular, not a spiral. So it will be something like this. Okay, we only have a ring. Okay, we only need to generate B field. We only need to generate B field in this path, but we need to control the magnitude of the B field accordingly. Yeah, because it will be like R equals mv over qb. So for this case, R should be a constant. This should be a constant. M is a constant. Q is a constant. But if we would like to make this V larger and larger, this B field should be proportionally increased with this V. Okay, so that this equation holds. So which means that at the very beginning, the V is low, so that the B field is also weak. But we try to making the B field stronger and stronger gradually, so that finally, it will be having a high velocity, so that high energy. Yeah, but it will not collide with the wall of this ring. Okay, otherwise we will stop. Okay. So the good point is that we only need to generate B field in the ring, although we need to control it precisely. But as much as the area is much larger, we don't need to generate the B field inside. Okay, so we need much smaller energy to do so. So it means that it can generate a much higher energy. Okay, like here we have a proton synchrotron booster, which accelerate the proton to 1.4 GeV. Okay, you can see 1.4 GeV is already more than 20 times larger than that one. And then followed by the proton synchrotron. So it's like a booster try to accelerate it halfway. Like when you drive a car, you try to shift gear, okay? You try to accelerate to a certain step and then enter this proton synchrotron and then to accelerate fully, okay, up to 25 GeV. Okay, if you're interested, you can try to check it out on the Wikipedia. I don't try to go through it. But, okay, maybe you ask why we need this kind of particle accelerator. So the idea here is like, yeah, for the physician, they try to know, okay, what is the fundamental particle? Okay, what is the fundamental particle in the world? So in the chemistry class, high school chemistry class, you should have learned, okay, so all the material are some atoms, okay, are some atoms. So the physician asks whether we can separate the atoms. Okay, so in high school physics or high school chemistry class, it also tells you that atoms is constructed by protons, neutrons, electrons. Okay, so and the question is whether we can further separate proton, neutrons, and electrons into even smaller particles. Okay. So how we can separate it? Okay, just like if you have a mobile phone, if you want to disassemble it, probably you can take some tools and then you can spend some time to really disassemble it in a few hours. And then a quick way is to you try to grab it and then you smash it on the floor and then it disassemble, okay, quickly. So the idea here is we try to accelerate the particle so that they collide with something else to see whether they can come up with some smaller pieces, okay, smaller fundamental particles. So keep in mind that, okay, this is 25 GeV. And then we also go back to this standard model here. The standard model here. Yeah, we can have some mass here. Okay, for the first generation, okay, this is like 2.2 mega EV per c square. Okay, so for the second generation, it goes up to 1.28 GeV per c square, and then this one 100 something. Okay, whether there are fourth generation, so far we don't know yet. Maybe if we have sufficient high energy particle, we may be able to find the fourth generation, but we don't know. We don't know. Yeah, because in the real world, what this standard model only can represent less than 10% of the particle in the mass in the universe, and then including the dark energy, including the dark matter, dark energy is only 20 something percent. Okay, so out of this standard model, there are still quite a lot of mass that we cannot explain. So maybe we need a higher energy particle accelerator, so that to find or to fix the standard model of particle. So that's why we need the particle accelerator. But of course, this is some hardcore physics stuff. I'm not trying to ask you in the exam. Just focus on try to calculate some variables is enough. Okay, so maybe that's all for today.